Okay, so now what we're going to do is we're going to try to understand in a little bit more depth this idea of moment of inertia. So the resistance that a rigid body presents to changes in its angular velocity. In other words, how much twisting force do we need to apply to cause a given angular acceleration? A lot or a little, that sort of thing. So the answer to that depends upon the axis about which you are rotating the rigid body. So for instance, suppose that I wanted to rotate this object about a vertical axis passing through its center of mass. So I'd exert a twisting force like this on it. And it's really easy to get this thing to rotate. It presents very little resistance to changes in its angular velocity. Okay? However, if I wanted to rotate it, say, about an axis passing through the center of mass, a horizontal axis like this, okay, then I got to exert twisting force like this. And here you can just feel it. It's much more difficult to change the angular velocity of this object to induce an angular acceleration. So the resistance of a rigid body to changes in its angular motion depends upon, well, about what direction, about what axis are you trying to change its angular velocity. Okay, so what we'll do is we'll start with the simplest possible example of a rigid body. That's this elemental rigid body that we talked about before, from which all rigid bodies can be constructed. Okay, so, and that's a point mass. Okay, this doesn't look like a point mass, but always think of these masses that we're drawing as point masses, okay, and of mass m, and that's connected to a pivot point with a massless rigid rod of length L. Okay. So this super simple rigid body can be rotating like this. It could be rotating like this. It could be rotating about any axis. So if it's rotating like this, it's around this axis, a vertical axis. If it's rotating, say, like this, then it's rotating around a horizontal axis like this. Okay, so we can rotate this elemental rigid body about any axis that passes through this pivot point. Okay? And so we'll consider the simplest case first. We'll consider an axis that's vertical like this. Okay, so it's a vertical axis, and we are imagining that we're going to exert a twisting force on this very simple rigid body, causing angular accelerations in, well, that direction. Okay, so this mass m, when the rigid body rotates, will move around in a circle like this. Okay, like that. Now, if the mass m is, say, rotating slowly, then its angular velocity radians per second is small. And remember that the angular velocity is a vector, and you just sort of curl your fingers in the direction of the rotation, and your thumb points in the direction of the angular velocity. So if it's rotating slowly, it has a small angular velocity in that direction. To say that the angular velocity omega is in that direction does not mean that it's moving in that direction. It means you stick your thumb in the direction of omega and your fingers curl in the direction of the rotation. And with a certain magnitude, so many radians per second is the magnitude of that vector omega. So if this rigid body is rotating slowly, then omega is a vector in that direction that is small. Okay, and if that object is undergoing angular accelerations, picking up angular velocity, then its number of radians per second is increasing, so the length of the angular velocity vector increases. Okay, so if this object is undergoing angular acceleration about this axis here, then the length of the angular velocity vector is increasing. So the change in the angular velocity vector from rotating fast to rotating slow, here it's rotating fast, here it's rotating slowly, the change is this vector minus this vector is a vector in that direction. So in this very, very simple case, the angular acceleration is also in that direction. And that's also the direction in which you are applying the torque. We are applying a twisting force. We're grabbing the object like this and we're twisting it like this. And so the direction of the twisting force is the direction of my thumb, is also the direction of the torque. Okay? And so we had, that the torque, the twisting force, is equal to the moment of inertia times the angular acceleration, alpha. Okay? In these really simple cases that we are dealing with in Physics 121. So in all of the cases that we deal with in Physics 121, it'll, well, almost always be the case that the angular velocity, the angular acceleration, and the torque are all in the same direction. They're all parallel to each other. Okay. Now, in the real world, omega and alpha and tau can be in different directions. Okay, and then it introduces a huge richness to the motion and the dynamics of rotation of rigid bodies and stuff like that. But for 121, you just need to think in these sort of relatively simple terms. Okay, so great. So the first thing to understand is that, and this is what we wrote down before, we're talking here about moment of inertia. So what is the resistance of this rigid body to changes in its angular motion? And so we had this result. I guess I'll put it down here, that the moment of inertia, is equal to the mass times L squared. And so the L squared here is extremely important to understand intuitively what's happening here. Okay, and you can do little experiments on your own here. So the point is that, how should I say this? The point is that this moment of inertia, the resistance to changes in angular motion, that increases quadratically with L, we'll say. Increases quadratically with increasing L. So what does that mean? How can we see that? Well, so here is sort of our model of this object here. So we're imagining that this piece of wood here is massless. It's not really, but let's suppose its mass is very small compared to the mass of this ball here. All right. So if I take this object and I try to say introduce an angular acceleration, so by applying a twisting force, I want to introduce an angular acceleration, say about an axis that's relatively close to the mass. Okay, so then I can see, oh yeah, not hard. You can feel it. It's not very hard to cause this thing to pick up angular velocity and then to slow down, then pick up angular velocity and then slow down. So it's not hard to change the angular velocity of this thing, but you only have to exert a relatively small twisting force, okay, like this. Okay. However, if I were, and that's with a small L, if I were to make L larger, okay, so make this massless rod longer, so in other words, move my axis of rotation further away from the mass, okay, then when you actually do this, you can feel it. It's way harder to introduce an angular acceleration, pick up angular velocity, then decrease, then increase, then decrease. It's way, way harder to do this. And it increases quadratically. So here, there's some resistance to changes in the angular velocity, and that's with some distance L. If I were to double L by going here, or triple L to be going here, it will be 9 times as hard, and I can feel it. It's way, way harder, okay? So the point is that the resistance that an object presents to changes in its angular motion does not just depend upon the mass of the object. It depends upon how the masses are distributed in that object. Okay, so when the mass of the object is close to the axis of rotation, the moment of inertia is small. When the masses are far from the axis of rotation, then the moment of inertia is large. That's a super important concept to understand intuitively. So let's try to sort of build our intuition with a couple of really simple examples. Okay, so what we'll take is, instead of this elemental, we'll add a second mass to this, make a slightly more complicated object. Okay, so we'll suppose we've got a mass. Yeah, okay, let's leave a bit more room. So we'll put a mass m over here. We'll connect that mass m to a massless rigid rod, and then to another mass, say 2m. All right, these are point masses. And what we're going to do is we are going to rotate this object. We're going to try to rotate this object about an axis that's vertical, but it passes through not this mass or this mass, but passes through the center of mass. So the center of mass is located about here. Okay, so the rod is of length L, the whole rod, and the center of mass point is located here. Center of mass point. It's obviously along the line connecting m and 2m, but closer to 2m. and we're going to rotate it about an axis, a vertical axis, passing through that center of mass point. Okay, so our first job is to figure out, well, where is the center of mass? Well, let's take the x-axis starting here and extend it out to here. And what we're looking for is a vector which points from the origin of our x-axis here, okay, to the center of mass point. And so there's only one component of the vector, it's just horizontal in the x direction. And so we're looking for xcm. We're looking for the distance from there to the center of mass point. Okay, so you'll remember that, how do we calculate center of mass? So center of mass is a mass-weighted position divided by the total mass. Okay, so x center of mass, how do I want to do this, is basically the sum of the masses, the sum of a mass-weighted position divided by the total mass. Okay, and so in this case we have a mass 2m located a certain distance away from the x equals 0 point. This is x equals 0. And how far is it? Well, it's just 0. Plus, we have a mass m located a distance full L away from x equals 0. Okay, and then I divide by the sum of the masses, 2m plus m. Okay, and so you can see that the x center of mass, these m's cancel out, it's just L divided by 3, so it's 1/3 L. Okay. And that's about where we've drawn it over here. So it's 1/3 of the full distance from 2m to m. Okay, so now we're going to grab this sort of baton with two masses at the end. We're going to grab this at the center, and we're going to exert a torque in that direction, which means we're twisting it that way. And we're wondering, well, what resistance does that object present to changes in its angular velocity? Okay, and so so this distance is 1/3 L. This distance is 2/3 L. Okay, and so now what we want to do is we want to calculate the moment of inertia for this object when it's rotated about its center of mass through a vertical axis. Okay, and so how do we define that? Well, the moment of inertia for a single mass located at perpendicular distance L away from the axis of rotation is just ml squared. Well, now we have two masses, so it'll be this mass times this distance squared plus this mass times that distance squared. Okay, so let's work that out. So this is, we can just write down sort of a general formula. So it's, mi, mass mi, times xi squared. The x distance, this is just, it's all just along the x-axis here. It's very simple. Okay, so it's that. And so what is that? Well, we have a mass 2m, and the distance from the perpendicular distance from the axis of rotation to the mass is 1/3 L. So times L over 3, and we square that. Square it, that's super important. Plus this mass, the second mass there, is little m, times the perpendicular distance from the axis of rotation to the second mass there is 2/3 L. And then we square that. And so we work this out. So this is 2 over 9 plus 4 over 9 is 5 over 9. Is that right? No, I'm sorry, 4 over 9 plus 2 over 9 is 6 over 9 is 2/3. I can't do algebra anymore. So this is 2/3 times ml squared. Okay, so what you'll notice is that the moment of inertia is always a mass times a distance squared times some numerical factor. In this case, it's 2/3 times ml squared. Okay, so that's great. So what? Well, now what we want to do is I want to demonstrate that, that's this situation, okay, where I've got, here's the center of mass of this object, and if I try to rotate this object, there's a certain resistance to changes in the angular velocity, okay, but if I change my axis of rotation, it gets a lot harder. So let's see that. Okay, so the next example we'll consider is this example. We're going to run out of room. Yeah, we can do it over here. So now we're going to say the same object. We have a mass 2m on one end of a rod of length L connected to a mass single m. And now, instead of rotating it about, trying to rotate it about the center of mass, we're going to move our axis of rotation to pass through the center of 2m. And we're going to grab it here and try to rotate it. So now our axis of rotation is here, and we're trying to twist it about here. Okay, so this distance here is L, and so we work out the moment of inertia for this object for rotation about that axis. So what's that going to be? So that's moment of inertia is, mass times distance squared, summed up. So we have a mass 2m times the perpendicular distance from the axis of rotation to that mass. Well, that's just 0. Okay, plus the second mass is m, and we multiply by the perpendicular distance from the axis of rotation to the mass, and we square it. Okay, and so this is 1 times ml squared. Okay, so you'll notice that it's clearly more difficult to rotate this rigid body about this axis, because its moment of inertia is ml squared, than to rotate the same object about its center of mass. This is only 2/3 instead of 1 times ml squared. Okay, so we see that. The next example we'll look at is, well, what if we rotated it about the axis on the an axis passing through little m? Okay, so now our situation looks like this. We have the same object, mass 2m, connected by a rod of length L to a mass little m, and we're going to rotate it about an axis that passes through little m. So we're going to go like this to it and ask, well, how much resistance does it present to changes in its angular velocity? So the moment of inertia now is equal to, same thing, it's the sum of mass times distance squared, perpendicular distance squared. Okay, so it'll be 2m, we have a mass 2m, that is located a perpendicular distance L away from the axis of rotation, L squared, plus we have a mass little m, which is located a perpendicular distance 0 from the axis of rotation. So that's times 0. Okay, and so this is just, this becomes twice ml squared. Okay, so we can see, this makes sense, because what you're doing is, in this case, you're rotating it about this end. If you try to rotate a point mass, it's effortless to rotate a point mass. It's only because all of those masses that make up that point mass are located at distance 0 away from the axis of rotation. I mean, just try this. Take a very, very small mass. It's really, really easy to cause that thing to rotate. This is a point mass, so it's effortless to get this thing rotating. But then you've got some object at distance L away, and so it's hard to get that object swinging around like that, okay? And so it's ml squared. But now all we've done is exactly the same situation, except we've replaced basically an m with a 2m, and so we should get exactly twice the number. Okay, so that should be clear. And then the last example we'll think about is this example, where we have 2m here, okay, same object, same rigid body, except now we are going to rotate it about an entirely different axis, not vertical like this. We're going to rotate it about an axis that passes along the rod like this. Okay, so this is the axis of rotation here. So we've grabbed the rod like this, and we're trying to twist it this way. Okay, so now in this case, the moment of inertia is equal to a mass 2m times the distance of that mass from the perpendicular distance of that mass from the axis of rotation. This is a point mass. It lies right on the axis of rotation. It's effortless to get that thing spinning. Okay, so that's times 0, plus the same for the other side. We have a mass m. What is its perpendicular distance from the axis of rotation? Well, it's right on the axis of rotation, which is 0. And so this is 0. Okay, so the point is, that's sort of like getting back to this situation. We've got an object like this. It takes effort to change the angular velocity of this object, some effort. But if I go on this axis, it's super easy, okay? Relatively speaking, super easy. Okay, and so that's that. Okay, so the point here is the moment of inertia, I, depends on the axis of rotation. Okay, so when you were talking about angular motion and resistance to changes in angular motion, it's much more complicated and much more interesting, right? Because when we're talking about the resistance of an object to changes in its translational motion, well, it's just the inertial mass. That's it, right? But when we're talking about rotating a rigid body, what's its resistance to changes in its angular velocity? Well, it totally depends on which axis you're rotating this thing about. Okay, and that's where this whole idea I mentioned at the end of our last lecture here, this moment of inertia is not just a scalar quantity, it's not just a single number. It's actually it's a matrix which has 9 components, like 3 by 3 kind of matrix like that. Okay, and so because you can rotate an object about all kinds of different axes, all right, through its center of mass. And then you can also rotate through axes that are not on the center of mass, and that are not passing through the center of mass, and we'll get to that. Okay, so that's the crucial point. The moment of inertia depends upon the axis of rotation, and so it's much more interesting, okay, than just translational motion. Another thing to say is, you should just do this right now. Just take whatever pen or pencil you have handy, and I want you to try this. I want you to put your fingers at the center of mass location and go like this. And you'll say, oh yeah, that's pretty easy to get this thing accelerating, angular acceleration, pick up speed, then slow down, then pick up speed, then slow down. It's easy to change the angular velocity of this object. However, simply move your fingers to the end. Move the axis of rotation from here to here. And whoa, you can feel the difference right away. It's a lot harder to change the angular velocity of this object. So I encourage you to do that right now so that you have a gut feeling for what's going on here. Okay? Yeah, so very good. So we talked a little bit about torque. We've talked a little bit about moment of inertia here. And, and so now we're going to do a calculation. I'll do a calculation, a more detailed calculation involving calculus, okay, of how you actually calculate moments of inertia. It'll be a really important example that leads us to something, a very important theorem called the parallel axis theorem. Okay, very good.